You know that old thought experiment about trying to fit the entire Library of Congress into, like, a briefcase?
That's a classic.
Yeah.
And it's always followed by someone telling you it's physically impossible.
Right. Well, looking at the sheer scale of modern large language models, LLMs, it feels less like a briefcase and more like we're trying to squeeze the entire internet into a single microchip.
That's not a bad analogy, actually.
We just keep hearing about them getting bigger and bigger, GPT-3, GPT-4, Llama with parameter counts in the hundreds of billions. But there has to be a physical limit to this, right? You can't just keep buying more GPUs forever.
That is exactly the wall the industry is hitting. I mean, it is a logistical nightmare.
Tell me about it.
Just to run a standard top-tier model, something with, say, 175 billion parameters,
Yeah.
you are talking about a server rack full of specialized hardware.
Wow.
It's like owning a Ferrari, but you need an oil tanker following you around just to keep it fueled for a trip to the grocery store.
Which is why today's deep dive is going to be a little different. We aren't just talking about how smart these things are. We're tracing the life cycle of making them actually usable and safe for the rest of us.
A very important distinction.
We have a stack of fascinating research here. A visual guide to quantization by Martin Grutendorst, the foundational Microsoft paper on something called LoRA, and a really complex study from Stanford and Georgia Tech on the unintended consequences of aligning these models.
It's a great collection because it really covers the whole spectrum. We start with the physics of shrinking them down.
Right.
Then we move to the efficiency of teaching them new tricks. And we end with the complex sociology of how they actually, view the world.
I want to start with the shrink ray, quantization. I looked at the Grutendorst guide, and honestly, it feels like magic, but I know you're going to tell me it's just math.
It is math, but it's very, very clever math. To understand it, you have to understand the problem. Standard models use 32-bit floating point numbers, FP32, for their billions of weights.
Okay, let's unpack that. Floating point.
Right. So imagine writing down a number like pi. In 32-bit precision, you're writing out a massive string of decimal places to be incredibly precise. A 70 billion parameter model using these numbers requires about 280 gigabytes of memory just to load.
Which is way beyond what you have on a consumer laptop. I think my MacBook has maybe 16 gigs.
Exactly. You're not even close. So the solution is quantization. In simple terms, we basically say, look, we don't need 50 decimal places. 2 is fine. We drop from 32-bit floats down to smaller formats, like INT8, 8-bit integers.
The analogy Grutendorst uses is an image, which I found really helpful.
That's the best way to visualize it, yeah. Imagine a high-resolution photograph with millions of colors. If you reduce that palette to just, say, 8 colors, the file size drops dramatically.
The image also looks terrible, right? It gets all grainy, you lose the detail. That's precision loss. So if we do that to a brain, doesn't the model just get stupid?
That is the trade-off. If you just chop off the decimals blindly, yes, the model breaks. So you have to be smart about how you map those big, precise numbers to small, simple numbers. You have techniques like symmetric quantization.
Which is like a mirror.
Right. You map the range of values symmetrically around 0. It's cheap, computationally. But then you have asymmetric quantization, where you actually shift the 0 point to better fit the data. It's more math, but it keeps the image or the model sharper.
But the source mentions this outlier problem. Apparently, one huge value can mess up the scale for everyone else.
Oh, yeah. Think of it like grading a class on a curve. If everyone gets a 70 or an 80, the curve is gentle. But if one student, let's call him the outlier, scores 10,000.
And you try to scale everyone based on that one score.
Everyone else looks like they cut a 0.
Right.
Precisely. In a neural network, if you have one weight that's a massive outlier, it stretches the range so much that the nuances of the other weights get lost when you compress them. The fix is called clipping.
Which sounds kind of violent.
It is, a little bit. You basically just cut off the extremes. You say, sorry, outlier, you're too intense. You sacrifice the accuracy of that one huge number to save the precision of the majority.
I love that. We are cutting the genius to save the class. Okay, so this brings us to some of the alphabet soup we see in the open source world. I see things like GPTQ and GGUF everywhere. What's actually happening there?
So GPTQ is fascinating because it's selective. It uses something called the inverse Hessian matrix.
Okay, hold on. Inverse Hessian, break that down for us without the PhD.
Think of a building. Some walls are load-bearing. If you take them out, the whole roof collapses. Other walls are just drywall. They're decorative. The inverse Hessian basically figures out which weights in the model are the load-bearing walls. GPTQ keeps those at high precision and aggressively compresses the decorative ones.
That makes perfect sense. So you aren't just compressing everything equally, you're keeping the important stuff sharp. What about GGUF?
GGUF is a lifesaver for people without massive GPUs. It lets you offload layers. So if your graphics card runs out of memory, GGUF lets the model spill over into your computer's regular system RAM. It's slower, but it means you can run a massive model on a normal gaming PC.
But this is where it gets really interesting. The source material talks about bitnet. We're not just talking 8-bit anymore. We are talking about 1-bit models.
That's the bleeding edge. It's actually a 1.58-bit model, technically. So standard models use complex decimals. Bitnet uses a ternary system. Every single weight is either 1 again, 0, or 1.
Wait, so the brain of the AI is just a massive grid of negative ones, zeros, and ones. How does that even work? How can it write poetry or code with just 3 options?
It works surprisingly well. But the real breakthrough isn't just that it works, it's what it does to the hardware. When a computer processes complex decimals, it has to do multiplication. And multiplication is expensive, it consumes energy, it takes time.
And with monocle 1 and 0 and 1?
You don't need multiplication. If you multiply by 1, it's the same number. If you multiply by 0, it's 0. Multiply by negative 1, you just flip the sign. So you turn heavy computation into simple addition.
That is wild. We are moving toward AI that runs on addition.
The stat that blew my mind is that a 13 billion parameter bitnet model is actually more efficient in terms of latency and energy than a standard model that is only 3 billion parameters. It's a complete paradigm shift.
So we've shrunk the model, we've packed the library into the briefcase using media of ones and zeros, but a base model is just a raw encyclopedia. It doesn't know how to be a legal assistant or a medical scribe. We need to teach it. And that brings us to the Microsoft paper on LoRA.
Low-rank adaptation, yes. This was designed to solve the fine-tuning bottleneck.
Because traditionally, fine-tuning is super expensive, right?
Prohibitively so.
Yeah.
Let's say you have your GPT-3 with 175 billion parameters. You want to train it to be a legal expert. If you do full fine-tuning, you have to update all 175 billion numbers.
Which costs a fortune in compute time.
And storage. This is the part people forget. If you have 10 different versions of the model, one for law, one for coding, one for poetry, you have to store 10 copies of that massive 350 gigabyte file. It's a storage nightmare.
So enter LoRA. The paper describes it as injecting trainable matrices. I really like the analogy we found about the Post-it note.
It's the best way to think about it. Imagine you have a massive printed encyclopedia. That's your pre-trained model. You want to add an update about a recent event. Full fine-tuning would be like rewriting the entire encyclopedia just to add that one paragraph.
Inefficient, wildly.
LoRA is like sticking a transparent Post-it note on the page. You freeze the encyclopedia, you don't touch the original weights, the toitheater. Instead, you inject these tiny little matrices, let's call them taller, into the layers. You only train the Post-it note.
So when the model runs, it reads the encyclopedia page plus the Post-it note.
Exactly. It combines the frozen weights with the learned update, and the efficiency gains are staggering. The Microsoft paper says it reduces the number of trainable parameters by 10,000 times.
10,000 times.
Yes. And it reduces GPU memory requirements by 3 times. But here's the kicker. The rank of these updates can be incredibly small. The rank, or dollars, can be as low as 1 or 2.
Explain rank in this context.
So rank effectively measures the complexity of the change. A rank of 1 means the change is very, very simple. The fact that LoRA works with such a low rank proves a profound theory, that the change in knowledge needed to adapt a model to a new task is actually quite simple compared to the model's total knowledge base.
That makes so much sense. The model already knows English, it knows grammar, it knows logic. Teaching it legal jargon is just a tiny tweak on top of that massive foundation.
Precisely. And practically, this means instead of storing a 350 gigabyte file for your new legal model, you store a 35 megabyte file. You can swap tasks just by swapping that tiny file.
That completely changes the game for deployment. You could have one base model on your laptop and thousands of these Post-it note skills you just swap in and out.
It democratizes access. You don't need a whole data center to train a specialized model anymore. People are doing this on their gaming rigs right now.
Okay, so we've shrunk the model with quantization and we've efficiently trained it with LoRA. Now we get to the part of the stack that feels less like engineering and more like, well, sociology. We need to make these models nice and helpful. This is the alignment phase. But the Stanford and Georgia Tech paper suggests this isn't a free lunch.
No, it is absolutely not. We use processes like SFT-supervised fine-tuning and preference tuning to turn a raw model into a helpful chat assistant. But this paper reveals that alignment acts like a filter, and filters are rarely neutral.
Let's look at the first impact they found, English dialects. They tested models on something called the MD3 dataset, which involves predicting the intent of speakers from the US, Nigeria, and India.
Right, and before alignment, the base models were sort of equally okay at understanding all three. They weren't great, but they were balanced. But after alignment, performance improved for everyone, which sounds good, but you have to look at the disparity.
The stat here is crazy. The gap between dialects went from about 1% pre-alignment to as high as 17.1% post-alignment.
That is the key takeaway. The model became more American. It got significantly better at understanding U.S. English, but only marginally better at Nigerian or Indian English. So relatively speaking, the alignment process just left those other dialects behind.
So we're optimizing for a specific user, likely without even explicitly deciding to exclude the others. It just happens. But then there was a flip side, the multilingual paradox.
This is one of those happy accidents in science. The researchers looked at models like Tulu and OpenChat. These were trained on data sets that the developers thought were mostly English.
They thought they were building English bots.
Correct. But when they tested them, alignment actually improved the model's capabilities in Arabic, Russian, and even Telugu.
How does that happen if they weren't trying to teach it those languages?
They analyzed the training data, specifically the shared GPT dataset. And it turns out users worldwide were pasting all sorts of things into ChatGPT. About 13.1% of that English dataset was actually multilingual.
So because the training data was messy and included accidental foreign languages, the model got smarter globally.
Yes. And the counterproof is the UltraChat dataset. That one was filtered strictly 99.9% English. Models trained on it that saw the performance in other languages drop. It shows that a little bit of diversity, even accidental, goes a very long way.
That is a huge lesson for data curation. Stop scrubbing everything so clean. But now we have to talk about the deepest issue in this paper, global opinions. This is where it gets a little uncomfortable.
This is where we move from what language do you speak to what do you believe. The study used a dataset called Global Opinions QA to compare model answers with survey data from countries like China, Jordan, Nigeria, and USA.
And what did they find?
They found a significant shift. After alignment, specifically reinforcement learning from human feedback, or RLHF, the models shifted closer to U.S. public opinion and further away from Nigerian or Jordanian opinions.
So before alignment, the model might have agreed with a Nigerian viewpoint on a social issue, but after alignment, it actually switches to the American one.
Exactly. It effectively learns that the correct answer is the American answer. And the researchers found the smoking gun in the reward model.
The reward model, that's the system that grades the AI during training, right?
Yeah.
What tells the AI good job or bad job.
That's the one. They probed the Starling reward model with a very simple question. User, where are you from? Assistant, I am from country.
Just changing the country name.
Just changing the country. And the reward model assigned significantly higher scores if the AI claimed to be from the UK, the USA, Canada, or France.
And if it said it was from the Middle East or Africa?
Lower scores.
Yeah.
Much lower. Specifically, nations like Iraq, Afghanistan, or the Central African Republic received the lowest reward scores.
Wow. So the AI is being mathematically penalized for saying it's from Iraq.
It goes deeper. The researchers correlated these reward scores with a Gallup poll of U.S. citizens' views on foreign countries. The correlation was 0.926.
That is almost a perfect match.
It is. It means the reward model, the very compass that guides the AI's entire personality, is calibrated almost exactly to the preferences of the average American citizen. It's treating Western origins and viewpoints as objectively better answers.
So what does this all mean? We have mastered the physics. We can use quantization to shrink a library into a briefcase. We have mastered the efficiency. LoRA lets us stick a Post-it note on the encyclopedia to learn new skills instantly.
But the sociology, that's where we're stumbling. We're building these incredibly powerful, efficient tools, but we're effectively hard-coding a Western-centric worldview into them. We aren't just building global intelligence. We're exporting a very specific cultural mirror.
It raises a massive question for everyone listening. If these models are going to be the infrastructure of the future used for education, law, government worldwide, is it okay that their moral compass is calibrated strictly by U.S. opinion polls?
And if we want true global intelligence, we have to ask, who is designing the reward function? Because right now, the AI is looking in the mirror and it's only seeing one part of the world.
Something to mull over next time you're chatting with your favorite bot. Thanks for joining us on this deep dive. And hey, Try to visualize those one-bit weights, just ones and zeros and minus ones, doing all that thinking.
It really is magic, isn't it?
See you next time.